Test, test, test. Okay, seems like the mic's working. Can someone comment on whether you guys can hear me? Great. Okay. Thanks all for coming to the lecture. So we'll start slow. So people may join in the next couple of minutes. So last time we talked about the proximal gradient methods. We also talked about the subgradient methods for the interest of solving non-smooth convex optimization problems. Okay, so today what we're going to do is to first finish the part of the lecture that we left out with last time, and then move on to help you guys with building more intuition about proximal algorithms. So that will require us to get a little bit deeper into the convex analysis. But this is also the lecture that you will get a lot of insight and get a lot of interesting properties about subgradients, subdifferentials, and have a more holistic view of everything. So after today's lecture, especially after we talk about the convex analysis part, and now you can generalize some of the things that you might have known from high school, and everything about convex analysis, you suddenly notice that it's so elegant and it's so interesting, and maybe it will become extremely useful for your future research. Okay, so let's continue with the lecture. Part of the lecture on the algorithms. So this is the slide that we stopped with last time. So we got to the point after we described the proximal gradient algorithm, and we talked about the several special cases of the proximal gradient algorithm that solves the composite optimization problem of the form f equals to g plus h, right? So when h is chosen to be different quantities, and then you recover many of the algorithms that are developed for more specialized purposes. For instance, when h equals to 0, you get gradient descent. When the non-smooth function h becomes indicator function, you get projected gradient. When g is equals to 0, so all you have is a non-smooth, potentially non-smooth function, then you end up getting the proximal point algorithm. And all of these are special cases, therefore you can apply the convergence guarantees of the proximal gradient methods to attain the 1 over k convergence or 1 over epsilon iteration complexity to get to suboptimality epsilon. Okay, so we see more participants joining the call. So for those who for those who have just joined the call, we are just starting. We are revisiting the last part of the lecture before we move on to talk about more convex analysis and to understand the proximal gradient descent a bit more. So we talked about projected gradient descent last time. We talked about the proximal point algorithm, which simply is to iteratively just run the prox operator, starting from some initialization and keep running the prox map update iteratively at the current location. So that's also called the proximal minimization method. Okay, so one concern is that even though the proximal point algorithm can be used to solve to solve the generic problem of minimizing a non-smooth convex optimization problem, it actually may require a lot more computation in every iteration. For instance, in general, like solving this prox update might be as difficult as solving the problem of simply minimizing h of z. What is really the difference? So the additional difference is this added regularization term. So with this additional term that you added to h of z, this actually makes the problem a lot more regular, a lot more well-behaved. So you can potentially solve, the hope really is that you can solve the prox operator a lot faster than solving the original problem. Okay, only in that case, when the use of the proximal minimization algorithm becomes becomes sensible. Like otherwise, you may well just use the proximal subgradient. Just use a standard. Just use a standard subgradient methods to minimize this directly. Okay. However, like in general, like even to solve the prox operator, it requires maybe an iterative algorithm to iteratively refine your solution. And at the end of the day, you don't really get the exact solution. All you get is like an epsilon suboptimal solution. So there are actually work that talk about how the errors in approximating this prox operator can leads to interesting overall like outer loop bounds on the convergence of the proximal point method. Okay, so a practical rule of thumb is that if you want to have like an inner loop algorithm that's run proximal operators in every iteration, you better make sure that this inner loop is solved to a numerical accuracy that are significantly better than what you require in the outer loop. For instance, if you want to get epsilon suboptimality in the outer loop, the inner loop needs to be at least epsilon, often like 10 times smaller than epsilon or 100 times smaller than epsilon, in order for the algorithm to behave well. So there are theory for this, but more generally, like these theory are more like a kind of approximations to what's really going on in reality. So it takes a lot of hand tuning in order to get this algorithm and to squeeze the best potential out of these algorithm when every iteration can only be solved approximately. Okay, so then there was this question is whether proximal gradient method is optimal. So we've already talked about this in the context of gradient descent when the non-smooth term h is not there. And then we, from Nesterov result, we know that the lower bound is say 1 over k squared or 1 over square root of epsilon. But the gradient descent upper bound is only giving you like 1 over epsilon or 1 over k convergence rate. So that's that's not ideal. So Nesterov also moved on to show that using a technique called acceleration, you can actually improve the algorithm. So it still remains more or less the same gradient-based methods. It uses only the gradients in the sequence of updates. On the other hand, when you use acceleration, you can improve the rate and you get a faster optimal 1 over square root of epsilon convergence rate. Okay, so let's like take a closer look at the algorithm of accelerated gradient descent and also the accelerated minimize like a proximal gradient descent for minimizing a composite function. Okay, so we'll be following back and Tabor, which is a generalization of the original Nesterov's accelerate optimal gradient methods to the proximal case. Okay, so here's the algorithm. So let's take a closer look at it. So again, you initialize at some arbitrary point. Okay, and then you basically you move like one step before you so that you actually have 2 iterates. And the only difference from the proximal gradient descent is that now you are actually calculating the gradient at a location that's not really your previous iterate. Instead, right? Instead, you're calculating this v as a linear combination of the previous 2 points. Okay, so this is your previous points, and you are, let's say that this is xk minus 1. Okay, and you just moved from xk minus 2 to xk minus 1 in the previous iteration. Okay, so what this is saying is that instead of calculating instead of taking the gradient step at this location before you take the prox step, you actually extrapolate a little bit more. You move a little bit more into the future, and then like that is the reason why this is called momentum. there's a little bit of momentum that's inherited from the previous iterations that moves you a little bit forward to someone that extrapolates this direction. So once you're here, right? So once you're here, then you move towards a gradient direction here. You move towards a gradient direction here, and then you take the prox. Okay, so this is V maybe V prime, and then from V prime you take the prox update. That moves you a little bit towards the next location, and that's xk. Okay, and in the next iteration, you're going to put together this xk minus 1 and xk, and then repeat the process. So that's how accelerated proximal gradient work. So the view of the momentum is a justification of a lot of the modern like deep learning optimizers that makes use of momentum to try to speed up the convergence of the algorithm in practice. But it is to be noted that this technique is shown to be working actually more or less only for convex optimization problems. And the benefit of momentum in solving non-convex optimization problems is really unclear, and it hasn't been able to clearly shown to be effective in the non-convex case, at least theoretically. And in practice, you do see that, and sometimes atom work better than, say, SGD with momentum works better than SGD, but in other cases, like SGD works better than SGD with momentum. So I guess the point is that the non-convex optimization is just too difficult to say too much things in general. But if we restrict ourselves to the family of convex optimization problems, then there are a lot of things that we can say for sure. In particular, for momentum, this is a particular instance where momentum can actually help you significantly, and then you gain an improvement from 1 over k to 1 over k squared. Okay, so this parameter k like is chosen very delicately. And also you need this learning rate tk to be chosen to be, say, 1 over L, right? To be 1 over L in order for this algorithm to work. And there's also a linear convergence version of the accelerated proximal method. Let me see whether this is a okay. So maybe there's a slide about it. So I'll wait until then. So this is what I mean by momentum. So if you choose the parameter of the momentum according to what's suggested by the optimal gradient, you can see that as k gets larger, this k minus 2 of k plus 1 actually gets closer and closer to 1. And when this parameter is 1, then you are more or less preferring xk minus 1. So this is saying that optimization keeps progressing, then you are becoming more and more closer to the standard gradient methods without without the additional momentum. Okay. All right. So so if we take lasso as an example, you can see that the acceleration can really help the convergence significantly. So this is a result of the subgradient method. So you can see that the algorithm really failed to converge quickly towards F star. On the other hand, like the standard proximal gradient improves this subgradient method significantly, but then it also got dominated by Nestor's acceleration based method that converges significantly faster. Okay, so it is to be noted that the acceleration methods are usually not a descent method, which means that it doesn't guarantee strict improvement of every iteration. So often what you see is something called a Nesterov ripple that makes progresses like this. So if you move this one a little bit larger and expand it, you can see that it sometimes looks like this. Yeah, but if you take the upper bound of this, then you will see that it actually converges a lot faster than the gradient descent, although it is not a descent method. Okay, so there's also like a method that was known to allow you to choose this learning rates TK parameter adaptively without knowing what the global gradient Lipschitz constant L is. But there is some distance that makes this approach not so satisfactory, because you cannot really once you hit a point where your step size is chosen to be really small, right? You cannot really go back up and then choose a larger step sizes. So this is like this has practical consequences in that if you use this method to choose the learning rate, you cannot really go back, and maybe at the end of the day you end up with using very small learning rates like throughout the optimization. Okay, if the function is I guess L strongly smooth or L satisfy L gradient Lipschitz everywhere, then this doesn't really matter, because at the end of the day, you know that this TK can never really be larger than L over beta, as one of the posts on Piazza rightly identified. Yeah, sorry, beta over L. So TK minus 1 is necessarily larger than beta over L. So this approach works if the function is L strongly smooth everywhere. But it is really the case when the function is not, when it has heterogeneous L at different locations of the space, then this version of backtracking line search is not really able to get a benefit out of a much smoother region than other regions of the space. Okay, so this is the exact statement of the convergence bound for accelerated proximal gradient. So we're not going to be able to prove this, but you can check and convince yourself that with this 1 over k square convergence rate, then you are getting the order 1 over epsilon square iteration complexity. Okay, so one remark about the technical insight of the accelerated proximal methods is that it is like the original version that's coming from Nesterov is more or less algebraic. So you don't get much insight from it at all, except the fact that it actually works. So this picture has been changed significantly in the past couple of years when there was a line of pioneering research in connecting connecting these gradient-based methods to ordinary differential equations. So once you do that, then the gradient-based methods can be thought of as a certain discretization of simulating discretization approaches of simulating the ordinary differential equation. Okay, so in particular, if the if the ODE looks like Tx equals to I guess minus gradient of fx at t, right? So this is an ordinary differential equation with time t. So this is a continuous equation. So it turns out that if you just discretize this appropriately, then you recover gradient descent. And if you massage this ODE a little bit more, you end up getting accelerated gradient descent and other methods, and with additional benefits of sometimes you don't have to know the unknown parameters. Okay, so I'll leave it there. So there's a large body of work on this, and now there are more than one method. So just now we described just one of them. There are more than one methods that achieves accelerated rate, and many of these other methods actually converge like similarly to Nesterov acceleration with a guaranteed rate, but more interpretable than the original proof of Nesterov. Okay. So so let's take a like specific example of the accelerated methods for solving the lasso regression problem that had been the go-to example that we run into for this composite optimization, and talk about FISTA, right? So the iterative soft thresholding algorithm is called ISTA. That's essentially just running the standard proximal gradient methods for solving lasso. And FISTA is just another name that's used by Beck and Tobol for the accelerated proximal gradient descent. Okay, so in this case, the prox operator becomes a soft thresholding, and then you are moving towards the direction of the negative gradient at this interpolation point at V that's coming from the two previous points. So I wanted to point out the computational benefit of doing FISTA with a more refined treatment. So notice that like with acceleration, now this algorithm converges faster, but is every iteration like having the same computational complexity? So turns out that it is the case, because if both these two are sparse, then V also needs to be sparse, and whatever that you get here is a vector, right? And the soft thresholding is simply like a linear time algorithm on this method. So in this case, acceleration actually does not incur additional computational burden on the algorithm, at least not too significantly. Okay, so if you look at the convergence rate, and it is also a lot faster, and you see this nice Nestrov's ripple in the FISTA estimates. So all these other lines that are shaded, that are in a lighter color, are just a visualization to showcase the different initializations with different input parameters. So you can see on many different examples at the same time, like with what's the performance of the algorithm. If you are like doing a kind of developing a new optimization methods, and this is one way that you can visualize with more convincing like empirical confidence band and how quickly our algorithm would converge on a variety of different input instances. Okay. So if we use logistic regression, it's also like the same case. Then the FISTA converges a lot faster than ISTA. Okay, so in practice, especially for statistical estimation problems, often like solving the single optimization problem is really not the thing that you want to do. Instead, you want to solve a sequence of optimization problem for a sequence of hyperparameters, and then you can decide with model selection tools to choose which hyperparameter is the best or is the most appropriate for the problem that you're solving, right? So this requires us to tune a bunch of lambdas. So there are approaches that can allow us to solve the entire problem a lot faster than simply taking the random or zero initialization and solve each one of these optimization problems separately. So that's called warm start. So suppose we first solve the problem for the largest lambda, lambda 1, and then use the optimal solution that we obtained from, say, lambda 1 to initialize that of lambda 2, and then keep solving that until the smallest lambda to our interest. And if you use warm starts, then it turns out that the standard gradient, standard proximal gradient method is actually not too much slower, or more or less on par. Suppose you use the accelerated gradient method. So it gets a benefit out of being a descent method in that it can only improve over the previous iterate, and especially when the previous iterate is already pretty close to the optimal solution, then the network of acceleration will satisfy an initial blow up, the increase objective function, a little bit before like descending following the network ripple. On the other hand, the gradient descent might have already been extremely close to the optimal solution to the next choice of lambda. This is especially the case when you are choosing a sequence of lambda that are very close to each other, and you make lambda 2 to be smaller than lambda 1 only by a little bit, and in that case, like using acceleration isn't really helping you too much. Okay, and there are other instances where every iteration of the accelerated gradient method can be significantly slower than that of the standard proximal gradient method. Okay, so take this example of matrix completion that we had previously. So recall that matrix completion tries to solve this kind of problem when we observe the movie ratings and we try to come up with an imputation of the matrix, and then also ensuring that this matrix is somewhat low rank, and we apply the relaxation of the rank constraint into a trace norm or a nuclear norm, like often denoted by this one as well. And this lambda is a mask that shows which ratings are actually observed. So this is a standard matrix completion problem. And we talk about the singular value thresholding algorithm for solving this, which is essentially a proximal gradient. Okay, so notice that suppose we use a standard proximal gradient, then we're moving along then we are moving along the previous iterate, which is already pretty much low rank, right? So we are moving towards this additional we're moving towards this additional having this additional interpolation, in getting this V can actually make the input a lot less sparse on the spectrum. So we can have the rank of V can be significantly larger than the rank of B, since we are doing interpolation of the two things. And that creates trouble because suppose the problem is extremely large and all we are able to solve is a so-called partial SVD or skinny SVD, which requires us to find the leading eigenvalue, an eigenvector, get rid of that, solve for the next one, and keep the greedily updating the skinny singular value decomposition. And the low rankness of this part of the decomposition of this matrix B is actually leads to very significant computational benefits. And that means that doing acceleration can actually hurt you in terms of how much time it takes to solve every iteration of the problem. And if you balance out the benefits that you get out of the faster convergence and the disadvantage of you in getting the solution in every iteration, so maybe the picture will be different. Like maybe it depends on which one is the more dominant in fact. Okay, so I'm using this example to demonstrate that in practice it is not a clear-cut decision to make that the accelerated methods with faster convergence rate, or in general any method with faster convergence rate, is always better than those with slower convergence rate. So you have to take into consideration of the end-to-end computational complexity and how accurate you want your final solution to be, in order to make the decision of which algorithm is the right algorithm for you. Okay, so so that wraps up the topic from the end of the last lecture. So today's lecture is going to be shorter, but more I guess more involved with mathematics, as we're going to be going back into convex analysis. We're going to be introducing new tools in the convex analysis, and then make use of them to interpret proximal gradient methods in various ways. Okay, so I think maybe now is a good time for us to take a 5 minutes break before resuming. Like, how does it sound? Okay, so we'll resume at 1:30. 136.
Hi, Professor.
Yes.
I have a question.
Yes.
On the one that you said that when k becomes really large and the entire thing is more close to xk, like more close to the normal proximal gradient descent.
So let's see. So let's go back to. Let's go back. So yeah. So you're talking about this slide, right?
Yes.
Okay.
When this equals.
Oh
to
yeah. Sorry. It's the other way. So it's using a larger momentum weights. You're moving a little bit further, so you're making this one larger. Yeah. So it is closer to you are making use of it is closer to making your new update more correlated with everything that had happened so far. So rather than making it closer to the gradient descent. Yeah. Thanks for catching that. Yeah.
All right, no problem. Thank you.
Yeah. Yeah, there's a request for me to post the slides of the upcoming parts for notes taken. Yeah, it'll take me like 3-4 minutes to post it on the website. Meanwhile, like if you go to the previous version of the course and hit I guess lecture 7 on the second part of proximal gradient, so that's more or less exactly the same for the purpose of note taking. Okay. So, okay, so it's 1:36. Let's resume the lecture. Unless you guys have any burning questions, so I'll start to talk about the second part of the lecture. Okay. Okay, let's move on. I guess I can maybe skip the recap. So basically, the story goes that so for smooth problems, we know that the gradient descent method, smooth and non-smooth. And so yeah, maybe it's a good time to slow down a little bit and to summarize things for a bit. Non-smooth and composite. Okay, for the smooth convex optimization problem, the gradient descent can be used to achieve 1/epsilon convergence rate, and the subgradient based method achieves like not applicable here, not applicable here. The subgradient based method can be used to achieve 1/epsilon square iteration complexity, but it is more general. It can be used to achieve this rate whenever your problem admits a subgradients, and you can calculate it. Okay, so what the proximal gradient method can do is to like I guess if we specialize it to the proximal point method, you can get the outer 1/epsilon everywhere. Yeah, but it really requires you to solve a more complicated update in every iteration. Okay, and finally, if you use accelerated proximal gradient descent, then you can get 1/square root of epsilon, and I guess 1/square root of epsilon and 1/square root of epsilon in all these problems. Okay, and in addition, like suppose we make a strong convexity. Yeah, so we'll revisit this later. Suppose we use strong convexity, assume additional that the function satisfy being M strongly convex. Then you can improve improve both these and that exponentially to something like c to the power of minus k or log 1/epsilon with the condition with 1 over the condition number parameter, and this L over M. Okay, and the acceleration is going to be able to help you by reducing the time complexity by taking a square root. So with acceleration, you can get square root of L over M log 1/epsilon. Okay, so I hope that summarizes the picture that we've seen so far. So we've only proving some of these results formally, but some of the other results will be proven as corollaries in the remainder part of this class. Okay, so one question that you will be working on in homework 2 is to prove the convergence of the proximal gradient descent. So as is instructed in the homework 2, you are supposed to make use of the notion called generalized gradient of f at this location x. So this is defined more or less as if this is a like trivial construction that's coming from the proximal gradient updates. But once you do this, you can rewrite the update rule into something that's more similar to gradient descent. And if you just follow the instructions of homework 2 question 3, so you'll be able to work out using almost exactly the same lines of arguments from our proof of the standard gradient descent, but replacing the gradients with the generalized gradient, and then you'll end up getting the outer 1/epsilon convergence of the proximal gradient. Okay, so that like even after you have worked it out, it may appear to you that this is something that's pretty mysterious. And why is that the case? And how is it that if you define this tricky generalized gradient in this way, then it naturally like works for solving the composite optimization problem. So in the remainder of today's lecture, we're gonna be providing some more insight into this problem. And in particular, so you'll get to see that this generalized gradient is not something arbitrary. It's actually the gradient of some function, and that function is closely related to the original optimization problem that you're solving. Okay, so before we get to that point, there are more tedious mathematics about the convex analysis that we need to talk about. But trust me, like these are definitely the more elegant part of the convex analysis beyond the technicality of things like closeness and supporting hyperplanes and so on. So these are things that you actually can help you gain more insight and generalization of things that you might have seen before. Okay, so what we'll be talking about, we'll be defining differential conjugates, or often also sometimes known as a convex conjugate. And then we'll take another look at the proximal operator and related objects such as Moho envelope and the smoothing approach in interpreting what the proximal gradient descent is doing. Okay, so first let's define the conjugate functions. So let's say that we have an arbitrary function that maps from R to the n to R. We can define its conjugate f star using this quantity. Okay, so you put fs here. You have this linear function y transpose x. Ultimately, this f star is a function of y. So can anyone tell me that why is the function f star necessarily a convex function? Why is f star convex? Oh, I guess, yeah, I guess the answer is just in the next line. So since this is a joint bivariate function of x and y, and y is the only term that we care about, and for every fixed x, this is the affine function in y. Therefore, this is doing pointwise maximum. Okay, and that by the composition, by the rules of getting convex functions, so that gives rise to a convex function, even if f itself is not convex. Okay, so how do we make sense of this? So here's one way that you can think about what the conjugate function is doing. So let's maybe substitute specific quantities of y into the equation and to see what we can get, right? So in the case when when y equals to 0, okay, then y equals to 0, then f star 0 is equal to simply max x minus f of x. So what does that give us? Minus f star, right? If fx is a convex, if fx has a minimum, and then taking y equals to 0 gives us the negative of the exact minimum. Okay, so now let's say that if we choose y, if we choose y such that f star of y is equals to 0. So this is the other place where we can assign something that's trivial to build intuition. So I guess what this is saying is that what this is saying that if this is a function f, okay, it's a function f, and this is the origin, and this is saying that you are getting this is saying that the function g x equals to y transpose x, okay, defines a hyperplane that that exactly supports this function f from below, right? So this is a supporting hyperplane of the epigraph of this function f. Whenever the right-hand side of this, whenever the conjugate function is equal to 0. So more generally, this conjugate function defines a maximum gap between the linear function that passes over the linear function g of x equals to y transpose x that passes through the origin, and if you just move it a little bit lower until you hit the point where this one becomes a supporting hyperplane, and that would be the corresponding the value of the conjugate function. So the difference between these two is going to be minus f star of y. Okay, so the first example is saying that, well, you are moving this horizontal line lower and lower until you hit this point. That's why you get minus f star, and the minus f star is, yeah, I'm sorry, I'm using f star in a confusing way. So f star now denotes the convex conjugate, but I'm also invoking this our notation of f star being the optimal solution. Maybe let's replace with FOPT. All right. Yeah, so this is just a more general a generalization of this observation when y is chosen to be 0. So you are basically trying to find the minimum of this function when the normal of this hyperplane is pointing towards different directions that are given to you by y, not necessarily the vertical axis. Okay, so I hope that makes sense to you. Okay. So let's maybe work out a couple of more examples about this Finchel conjugate. So let's start with the simple quadratic function, right? And then just work out maths to convince you guys that often this is something that you can calculate. So again, f star of y by definition is equal to max get rid of x and y transpose x minus f of x. Right? Since this f is a convex function, the minus f is a concave function. A concave function plus a linear function gives you a concave maximization problem. So we can basically set the gradient to be 0 and set the gradient to be 0, and that gives you the optimal solution. So if we work it out, we get the gradient to be y. In this case, let's take the f to be the quadratic function. So the gradient would be y minus q of x, right? Assign that to 0 would give us x equal to, since q is positive definite, it is invertible, you get q inverse of y. Okay, and let's substitute this x equal to q inverse y into the objective value to obtain the conjugate. So f star of y is equal to y transpose q inverse y minus y transpose q inverse transpose q inverse y. Since y is a symmetric, right? Then its inverse is also symmetric. Then having this transpose or not doesn't really matter. So you can cancel these two out, and that gives the minus half of y transpose q inverse y. Wait, why am I missing the half here? Oh, okay. So this is minus half of this. So at the end of the day, you get the positive half y transpose q inverse y. Okay. So let's take another example. So if fx is an indicator function, then its conjugate simply by definition gives this. You can't simplify this a little, even further because we're not specifying what this convex set is. But this is by definition the so-called support function. the intuition about support function is a little bit unclear. You can see that more from the epigraph interpretation that we had previously about hyperplanes that are passes through origins and whether it supports a particular convex set. But let's take a specific example of this convex set so that we can gain some intuition. Okay, so let's take this fx. Let's maybe work it out from the other direction. Let's take f of x to be an arbitrary norm, right? And then its conjugate, the conjugate of this norm function f of x. So let's work it out. It's going to be the maximum of y transpose x plus the norm of, okay, so this is f star of y. Okay, so let's take the subdifferential calculus here, and then take the so that we know 0 is in the subgradient. So what is the subdifferential? What is the subdifferential of this? So you can apply the adding rule. And make this. All right. So actually minus. So let's be a little bit clearer. And this becomes a minus minimum of x minus y transpose x plus. Okay, so now this becomes a convex optimization problem that you can apply the subdifferential rule. So by the subdifferential rule, you get a gradient of the first term. Ignoring the first minus sign in front, you get a gradient of the first term, which is just y, and plus the subdifferential of x. Okay, and you know that 0 is inside here. But what is the subdifferential of a norm? From the previous lecture, we've seen that the subdifferential of the norm is the indicator function into its dual norm, right? So this condition is equivalent to, say, y is inside the set of all points where this point satisfies dual norm is smaller than 1. Okay, and that that gives us the its conjugate function f star being the indicator function of this dual norm of z smaller than 1. Okay, so in the next slides we'll be seeing like a property of Fincher conjugate that if f is convex, then f conjugate and take another conjugate is equal to f. So therefore, now that this is an indicator function, and notice that notice that from this calculation, when this convex set C is chosen to be just a norm ball, right? And then the conjugate of that gives rise to this. And what is this? This will be the maximum of x inside the ball where the dual norm is smaller than 1, y transpose x, and this is by definition the dual norm of this dual norm that gives back that gives you back y original norm. Okay, so again, so a norm is dual to its dual norm, then the dual norm's dual is back to the original norm. Okay, so when thinking about the dual norms, think about LP norm. L1 norm is dual to L infinity norm. L2 norm is self-dual, and so on and so forth. Okay, and then the, so now everything becomes together, and with this you should understand this indicator function, support function, in a specific example, and also you have a refresher of the definition of the dual norm and the definition of the conjugate and how they are related to each other. Okay. So now let's go to the properties of conjugate functions. So the first thing, so we've already talked about that if f is a convex and closed function, then the 2 times conjugation gives back to the original function. Okay, so let's talk about other of the properties of the conjugates, right? So first of all, there's this Finch's inequality that's hugely useful. That says that you can upper bound the inner product of any 2 points x and y using using the sum of f of x and f conjugate of y. Okay, so so let me try to connect this to something that you might have you must have seen before from maybe middle school or high school. So first of all, there's this basic inequality that essentially is a inequality between algebraic mean and geometric mean, right? So this is saying that 2 xy for any non-negative xy, 2xy is smaller than x squared plus y squared. So actually you don't need non-negativity here, and this is always true. Okay, so so this inequality can be generalized to so-called Yu-Xiang's inequality, which you might have learned. So for now, think about x and y are both like a scalar. So in Yu-Xiang's inequality, you can bound x, y using a pair of conjugate conjugate numbers p and q. So you can bound this by x to the power of p over p plus y to the power of q over q. Okay. In this case, provided that the p and q are both larger or equal to 1, and also it satisfies this conjugate equation. Okay. For any, this applies to any x and y that's non-negative. Okay. So so I argue that the Finch's inequality is a generalization of these 2 things that you've seen and maybe used and might have a lot of experience before. Okay. Let's see why is that is the case. Okay. So let f of x to be x to the power of p over p. Let's work out what this f star is, right? So f star of y by definition is maximum of x, y. So now that everything is scalar, so we can simply take the standard product of the 2 minus xp over p. Okay, since like there's a domain, right? So it needs to satisfy that x larger than 0. And the domain of this conjugate is also x larger than 0. But on the positive domain, then we know that this is a concave maximization problem. Then we can solve it by evaluating the gradient and then assigning it to 0. So the gradient is y minus, let's apply the rule of derivatives, and then p xp minus 1 over p. These 2 got canceled out, and assigning this to 0, we get x equals to y to the power of p minus 1 over 1. Okay, so let's substitute this back to the original objective functions that we are maximizing. Then we get we get f star y to be y to the power of p minus 1 p plus minus p of y to the power of p minus 1 p. And these 2 can be combined into 1 minus 1 over p, and y p minus 1p. So notice that when q is chosen to be the conjugate of p, then this is the same as y to the power of q over q, as expected, and that gives us how do we specialize the Finch's inequality into Young's inequality. And as a matter of fact, this is Finch's inequality, often also known as the Finch-Young's inequality. Okay, so there are more interesting properties of the conjugate functions, and specifically, so it is closely related to the subdifferential. So if f is convex and close, then if x is in the subdifferential of its conjugate function, this is equivalent to saying that y is in the subdifferential of a function f at x. Okay, you can see this a very nice symmetry in these two equivalent representation, and that actually gives us the fact that whenever the equal sign is true in Finch's inequality, it must be the case that x satisfy this and y satisfy this. Okay, so whenever we take equal in Finch's inequality, okay, that's neat, right? So it's not really clear like why this is the case, but it naturally follows from the beauty of convex analysis. So subgradient isn't something that's artificial, and like after all, it's closely connected, and it's a generalization of something that's more fundamental, as fundamental as the inequality between algebraic and geometric inequality. Moreover, yes, there's a.
I have a short question.
Yes.
So the thing just written down to express the connection between the Finch's inequality and the Young's inequality. Does that only applies to the univariate case, or is this x and y, they are both vectors and still that is still fine?
Yeah, when you have vectors, then I mean my knowledge of Young's inequality is this univariate case. If you change it into the vectors, then x to the power of p needs to be replaced with norms, right? So that's something that also applies, and you can work out the details. And I would say that if like, why not just directly learn like Finch's inequality? Okay. And then that becomes applicable, and often in many of the proofs that you're doing, it boils down to find the right convex function to decompose this x transpose y appropriately. That gives you the tightest rate. Yeah, good question.
Yeah, it's like for the Young's inequality, you need this xy to
right
to actually be non-negative, right?
Right.
For Finch's inequality, for any xy belongs to Rn, this is always true. So
yeah. So you can you can add absolute value and then sum across the coordinates.
Okay.
Which is saying that basically if x is a vector, so this is a p's power of the p norm, and then q's power of the q norm, and that's something that I encourage you to work out, and maybe share your finding with your classmates in the MTS.
Okay. Thanks.
All right. So now suppose the function of two variables can decompose into f1 and f2. So this is like a Cartesian type of decomposition, and f1 depends only on the first part of the parameter, and f2 depends only on the second part of the parameter. If that is the case, then you can calculate the conjugate function by simply doing this. right? Yeah, I hope like this list of properties like convinces you that the Fincher conjugate is something that's of great interest, and it is also of mathematical beauty. Okay, so now let's go back to the proximal operator. So we've defined the prox operator to be the argmin of this convex optimization form, right? So notice that this is argmin. So the output is one of the solution of this minimization problem. But notice that if this function f is actually convex, this additional term ensures that this optimization problem has a unique solution. And why is that the case? The fact that there's an answer saying that they are both convex, but the fact that the whole thing is a convex function doesn't really guarantee the uniqueness of the solution. It tells you that, this is a convex optimization problem, but it doesn't tell you that the solution is unique or the set of solution is a singleton. Maybe along the lines of like what are the conditions that we know about whether the solution to a convex optimization problem is unique? Yeah, that's great. Yes, the answer is that the first term is a strongly convex term. So adding this to any convex function will make the whole thing strongly convex, therefore strictly convex. Therefore, the solution will be unique. So in that case, this inclusion sign will be equal. Okay. So again, notice that this is argmin. So we can also define the objective function value of this and then make sense of the objective function value of this problem that we're solving in the prox operator. Okay, so this is what we call the Moho envelope. So the reason why this Moho is pronouncing this funny way is that it's not really. So this R is this Ch sound from French German. So that's the reason why people are pronouncing it weirdly. I'll try my best. Like I don't know either languages, but I'll try to stick to the convention. So the Moho envelope is defined as just the objective function value of the minimization problem that you solve in the prox. Okay. If you just plug in the prox, then you will see that it becomes something that's a constant. Yeah, sorry, not a constant, but it's something that's a sum of the two things involving the prox operator. Okay, so you can define the Moho envelope for any convex function. So the idea is that for any convex function that's not necessarily smooth, so it has a Moho envelope that is actually smooth. So the smoothness parameter depends on the t parameter that you use. Okay, so let's give an example so this point is clear. Oh, I just noticed that there's a question about maybe 2 slides before about the possibility of a minus sign. Yeah, so let's see where it is. I see. I think the remark about the minus sign is about this, right? Well, yeah, I think it's actually making sense, right? So suppose you are out of the bound, and then this is gonna bring you to the negative infinity. therefore, if you toggle the negative infinity to positive infinity, you end up getting this indicator function of 0, positive infinity. All right. Okay, so let's come back to the example of Huber function. So we talked about this before. So what Huber function is it's something that people come up with from the robust statistics literature that tries to get the benefit of both the L2 and L1. So recall that L2 is just a quadratic function that tries to that is like very nice, it's smooth everywhere and differentiable, and it's a bell-shaped like function. And L1 norm, like this is square L2 norm. And L1 norm is absolute value function that is pointy at 0. So the advantage of this L1 function is that it is robust. It doesn't penalize whatever that deviates from the median by too much. Whereas L2 norm penalizes that quadratically, L1 norm penalizes it only in absolute scale. Another reason is that this L1 norm satisfies a property that it is a closest convex relaxation to the L0 norm. That's why people use it as a surrogate of to induce sparsity. Okay, so the idea of Huber function is that you want to get the benefit of both of these two. So you want to inherit the robustness of L1, but also the differentiability and smoothness of L2. Okay, so how the Huber function is constructed is a piecewise function that is like quadratic when you are close to 0, and then minus delta and delta, and then you shoots up linearly as the two ends. So it's like in some sense a hybrid between the square L2 function, between the quadratic function and the L1 function that tries to get the two objectives at the same time. Okay, so we can actually rewrite the Huber function naturally as a Moho envelope of the L1 function. So in the one-dimensional case of the absolute value. Okay, so this is something that we are already very familiar with from the previous lecture when we talk about the proximal operator. So so the optimal solution to this is a so-called soft thresholding. Okay, so whenever x is smaller than between minus delta and delta, then the optimal solution will be 0. And whenever x is outside the region minus delta to delta, then you are shrinking this input towards 0 by a factor of delta. Okay, so if we substitute these two back to the equation. Okay, so let's first substitute y equals to 0. Then naturally we get half x squared. That gives rise to the first leg of this definition of Huber function. And suppose we substitute y star equals to x minus delta sine of x. Then we get half delta sine of x squared plus delta of I guess x minus delta sine of x absolute value. So the first term, since the sign is always minus 1 or 1, is half delta squared, and the second term, since x is outside the minus delta to delta region, so move it closer to 0 will reduce the magnitude of it. So that gives us delta x absolute value minus delta. Let's collect everything together. You will see that you end up getting this quantity that's stated in the second leg. Yeah, so instead of being just an arbitrary hybrid of the two functions, it actually comes out of the Moho envelope, and it can be natural to view the Huber function as a smoothed version of the the one norm. Okay, so this picture illustrates it all. Okay, so by the way, Yu-Xiang's notes are really great, and he go in depth into the convex analysis and explain all these concepts of proximal operator and the Moho envelope extremely clear. And I learned a lot of these materials from his guest lecture in Carnegie Mellon, where he was a like postdoc over there. Okay, so again, let's talk about properties of the Moho envelope and the prox operator. So like we've already talked about, you can think about the Moho envelope as a smoothing of a given arbitrary convex function that's potentially non-smooth. Okay, so you pass in f, you set the parameter t, and this becomes a smooth version of it that's that's differentiable and has I guess bounded second derivative everywhere, like if second derivative exists. Yeah, so this is a quiz question for Huber function. Is the Huber function smooth? What's the smoothness parameter? It's the L smooth parameter. And second, is it twice differentiable? Yeah, if you have an answer here, like feel free to just post that in the group chat, or later post that on Piazza with your work. Okay, so let's go back to the properties. So first of all, this is a smoothing, and it's called Yoshida-Moho smoothing. And we can smooth this and more concretely prove that if you smooth this for any convex functions, then the envelope is at most 1 over T smooth. Okay, so we'll see this later after we talk about duality. Okay. The second thing is that it actually preserves the optimal objective value. So the minimum of f of x is the same as the minimum of its Moho envelope. So that's nice, right? So that means that if we can minimize the Moho envelope, then we also can minimize the original function. So why don't we minimize the thing that are that's actually smooth? Okay, and thirdly, so it also preserves the argument that minimizes the objective function. So suppose x minimizes f, then like this is equivalent to say that the same x also minimizes its envelope. Okay, to see this, consider this function with multiple with a multiple minimum. Okay, well, maybe this function looks like that. Okay, so it's not really a convex function, and its envelope is going to look like something as we've seen before, and then you have some quadratic term here. This part's already pretty smooth. It's gonna look like something like that, and you can see that after you smooth out this pointy point, and all the argmin, all this x star remain like where they are for the smooth version of the problem. Okay, so so the fourth property of the Moho envelope is not it's actually very interesting, but it's a little bit more technical to prove. So you can show that the gradient of this smoothed function is actually closely related to the proximal operator in a sense that you can write the gradient of the Moho envelope to be exactly this. And does this remind people about something? Like we talk about the algorithm, the proximal gradient descent. We talk about the proximal point method. Yeah, so exactly. So this the gradient of the envelope actually corresponds very nicely to the Nesterup's gradient map. So you can interpret the proximal point method to be keep running the gradient descent on the envelope of a smooth function, which explains naturally the improvements from 1 over from 1 over square root of from 1 over epsilon square to the of the subgradient method to 1 over epsilon of the gradient based method, because it is smooth. That's the right thing that you would expect. And finally, if you keep solving these proximal iterations, then the only fixed point that satisfies this condition is actually the optimal solution that minimizes the original f. So that's a property that motivates the design of the proximal point algorithm, that keeps applying the proximal iterations again and again and again until it converges. Okay, so there's I guess there's one point that I'd like to make about this gradient thing. Okay, so think about this alternative writing of this proximal term. So think about this alternative writing of this Moho envelope. So m of tf at x, this is equal to 2t x minus prox t of f by simply substituting its optimal solution into it. Okay, so taking the gradient of this function is not really straightforward at all, because the prox thing is something that's highly nonlinear, and taking the differential in the face of minimization is not something that's easy to do. But if you look at the final form of the gradient, it is as if you simply treat this prox to be a constant and then take only the gradient with respect to x in the first term, right? So let's do the exercise. If we just like abuse calculus and then calculate it out, then calculate the gradient with respect to only this this is the first term, then we get t over 1 and x minus prox t f x, right? So that gives that. So another connection that I want to point out is a special case when this f is an indicator function to a convex set. So when f is indicator function to a convex set, and then we know that in this case the proximal map becomes simply the projection to the convex set. Okay, in which case we know that the gradient looks like x minus project to c of x divided by t. Okay, so recall that in the previous slides, and I think in the previous lectures, in one of the lectures when we talk about the distance to convex set function, and then we talk about how this distance to convex set function is actually differentiable when x is outside the convex set. Okay. Distance to convex set is equal to the minimum of such that y is in convex set. This is equal to the without the square. This is equal to x minus project x to c. Okay, and we've shown that its gradient is actually its gradient of this function is actually equal to the to x minus project C of x divided by x minus project. Okay, with this additional normalization. So this form is also related to the gradient of the Moho envelope with an important difference in that this gradient is normalized, right? So what is the gap there? So the gap really is whether there's a square here. So if you add a square here, then this actually answers. This is actually one way that you can answer one of the quiz questions that I gave you in that lecture. And what if this distance to convex function is squared? And then if you take the gradient, you will end up getting this exact form. That's a special case of this application of the gradient of a Moho envelope. And we know that when you have a square term there, it becomes differentiable everywhere, not just differentiable when x is outside. Okay. There are more properties, like even more interesting properties about Moho envelope and Prox operators. Okay, the first is the so-called Moho decomposition. So you can think about it as a generalization of, say, the projection of a vector into a subspace X and its corresponding orthogonal complement subspace. So we've done this for many times when we learn physics. So when the little ball is rolling downhill on this, and then we were asked to analyze the force, and by decomposing it along, decomposing the force of this gravity along this direction and that direction, right? So you can always do this kind of a projection of this vector of gravity into the directions that are perpendicular and parallel to a given subspace. And the Moho decomposition here is a generalization of this decomposition that applies to an arbitrary convex function f. Okay, so I guess I'll give an example in this additional note to show you like how this could be meaningful even in the cases when this f is an indicator function. So let's say f x is an indicator function where C is, so instead of a subspace, now let's consider like a convex cone. Okay. Let's consider a convex cone with with a pointy end at the origin. Okay. Let's say that this is a convex cone, and everything inside here, this is a C. Okay. So what is a conjugate of that? So the conjugate of this function by definition is a max x y transpose x minus indicator x. So notice that whenever there exists an x in C such that y transpose x is positive, then f star of y is positive infinity. Because whenever that happens, then you can always blow up and increase the size of x in the cone, since the cone has like it's unbounded towards the direction that it's pointing to. Okay, and whenever what is a complement set of that? Whenever otherwise, then this is saying that for all points in this convex cone, this direction pointing by this vector y is actually take the inner product and the angle is larger than 90 degrees. So let me visualize that for you. So so this is saying that we need to consider y that's on the left-hand side of this, and we also need to consider y on the left-hand side of this. Okay, so finally so that gives rise to I guess a dual cone of this additional cone. This is a C like it's actually the dual cone is something that's slightly different, but let's just call this a C star. So it's also another cone at that point at the same location, and all the whenever y is inside this cone, then the minimum of this conjugate function by working out this optimization problem will give you f star of y equals to 0. And what does it say? It checks the definition of this f star is actually an indicator function of this C star. Okay, so now let's use a different color to describe the Moho decomposition. So for any given point, then we can decompose it. So suppose the point is right here, then suppose this point is right here, then y is simply equal to the projection to C of y. And the projection to C complement will give you 0, right? And suppose you are right here, then you only get like C, the projection to C star, and the other part gives you 0. Suppose you are here, then this is essentially the same as a projection to the corresponding subspaces. Then you can decompose y into PC of y plus PC star of y. Okay. All right. So this kind of thing can be applied beyond projection, and then you can do this for any proximal operators and with any pairs of conjugates f and conjugate convex functions f and f star. Okay. So So when you combine this decomposition with a gradient calculation in the previous iteration, in the previous slide, then you can just substitute this into this equation here. Then you get something that's more like more concise. You can work out that the gradient of Moho envelope is actually the prox of its conjugate at the same location. That's pretty elegant, right? And the second additional property of the prox operator is that is that like if you take the multiple convex functions and add them up, like sorry for the typo here, there's an fi, then there always exists another convex function g such that the sum of the prox is equal to the prox of the sum. So the tricky part is that this is an existential kind of statement, which doesn't tell you like how do you construct this convex function g from S1 to F1 to Fm. So there are additional conditions that you can make such that you can work out the exact form of g. But even if you do not know what this g is, you can what this theorem is saying that you can calculate the prox operator of that unspecified g. By calculating the prox of each F1 to Fm to induce some kind of structures that are given to you simultaneously by all of the convex functions. So one example would be that you can simultaneously minimize this is a like difference operator of a vector that takes the adjacent differences and then add everything up plus x1 norm. This is like a regularization term that induces property that wants this signal x to be simultaneously piecewise constant and sparse. And people give this a name. This is called fused lasso. I would add it to be sparse fused lasso because this term is a sparsity term. And you can also do the matrices when you want simultaneously the low rank and sparse. You can design a function like this. So what this is saying that by this proximal averages, there exists another function which prox operator is the same as the prox operator of these two, which means that you can actually do this and then apply the proximal gradient method to solve this problem, and then like which essentially is a solution to this unspecified G. Okay. So lastly, just like the projection operator, the prox operator is also a non-expansion. Okay. So this is how the non-expansion is defined. So in fact, this is a little bit stronger than the non-expansion that we talked about in the previous lecture. So previously we talked about the non-expansion that's implied by this property, which looks like which is implied here by simply applying the Cauchy-Schwarz inequality. Okay, and then cancel the square with the right-hand side, then we get the non-expansion of the previous of our previous description. Okay. So there's some more to it. Okay, so let's talk about the subdifferential a little bit more. So so the subdifferential is a mapping from a point in the domain of F to the set to a set that to a subset of the domain of F. That's called the subdifferential. Okay, so this is a point to a set. Okay, so so this is not really so if you take the inverse of it, I guess you can take the operator point of view and consider this to be a function to another function, from a singleton set to this set, and then you can define something that's pretty central at the operator theory. You don't have to know this. Like I personally don't know operator theory beyond the context here. So just treat this as something like the one's topic, and that helps you to build intuition. So we are not going to be able to talk about the detailed calculations of this operator theoretic framework. But there's an operator that you can define called a resolvent. That's simply that's simply adding a diagonal operator to this to this subdifferential operator, scale it appropriately, and then take the inverse. Okay, so this mapping is often like a function. So if you passing any point, it maps it to a unique point rather than the subdifferential, which is a point to set a function. Okay, so it can be seen that the prox operator is actually the same as applying the resolvent operator to a given point. Okay, so we can work it out from simply the first order optimality condition based on the subgradient. So this is something that we've done for many times now. So by the first order optimality condition, if X star is optimal, then it satisfies this property that you substitute this Y to be X star into here, you take the gradient, you take the subdifferential, and then 0 needs to be within the set of subdifferential. If you just move X to the other side, and you see that you see that this actually satisfies this set inclusion condition. And now let's make it operators by combining this identity. So this X star is the identity operating on X star itself, and then combine the two operators together, and that gives us I plus this partial F on X. So think about this as I guess think about this as a infinite dimensional matrices, infinite by infinite matrices, like matrix. So when we talk about operators of transformation of functions to other functions, and you can think about a function as a vector, and then the operators will be matrices that you act on functions. And the beauty of doing that is that once you go to the infinite dimensional, everything becomes linear. So now that this becomes a like a linear in the function space, and you can take the inverse of it, and then that recovers x star is equal to this. Okay, so that shows that the prox operator actually gives you the output of the resolvent. From this point of view, then we can make it clearer that the proximal point algorithm that keeps iteratively apply the prox operator can be thought of as a fixed point iteration in the operator theoretic sense, that you keep applying the same operator again and again and again and again, and if you just move things around for a little bit by adding xk and subtracting it from the operator, then you recover something that looks like this. And that gives you the generalized gradient point of view, and also by the gradient of the Mohl envelope theorem, then that says that you are essentially doing the standard gradient descent on the smooth objective function. Okay, you can see that there are multiple ways of making sense of the algorithms that we talked about. And notice that this other property of the Mohl envelope is saying that this Mohl envelope satisfies this 1/t smoothness. So the choice of this learning rate happens to be, so when L is equal to 1/t, then the choice of this learning rate is naturally like 1/L. Right, so it even gives you the largest possible learning rate from our gradient descent convergence theorem. So now let's talk about the proximal gradient algorithm. So this will be the bottom line of this set of lectures. So recall that this is as we described as this algorithm. To start with xk, you iteratively decompose your updates into two steps. You do descent, you project it back. You do descent, you project it back to the feasible region in the projected gradient case. In the proximal gradient case, you basically descend and then take prox, descend and take prox. You alternate between these two steps again and again until it converges. Okay, so if we write it in a fixed point iteration form in this operator theoretic form, then we can write this update rule to be first a linear operator that takes a gradient descent, right? So this is like a transformation of this input. And then the prox term can also be written using our the thing that we've proven earlier, since it is the same as a resolvent operator. So then the fixed point iteration becomes like becomes simply this. And previously we've talked about the majorization minimization framework. And you can also think about this as solving a smooth version of the majorization minimization objective. So after we take the linearization of this smooth function f by doing the first order approximation of that with t chosen such that we have always a valid upper bound, and then let's smooth the whole thing, right? We can smooth the whole thing by constructing the Mohl envelope of this function in the smooth majorization objective, and that gives us f linearized plus h at xk. So the proximal gradient algorithm can be interpreted as simply taking the gradient of the smooth version of this non-smooth objective at every iteration. So you are using a different Mohl envelope in every iteration to construct these sequences of gradient. But thanks to the majorization minimization framework, that allows us to derive like an iterative algorithm that actually works. Okay, in summary, so even though the proximal gradient methods seem mysterious, it's actually something that follows from simple principles behind the thing. So when we have a smooth optimization problem, a non-smooth optimization problem that's difficult to solve, so the idea is that why don't we smooth it? And the Moho-Nemelo provides a way for us to do so in a way that gives us that retains the properties of the optimal objective function value and also the optimal the optimal the optimal arguments that achieves the optimal criteria. And the proximal gradient can be thought of as combining the idea of local quadratic approximation and invoking the majorization minimization framework and the smoothing that's coming from the Moho-Nemelo. And with that gives us exactly the proximal gradient algorithm. And moreover, like if you write everything as operators and as linear operators in the function space, then we can write many of these as fixed point iterations. So the beauty of fixed point iterations is that it is easy that we construct some kind of a contraction map. So notice that we talk about non-expansion. So there are often cases, there are sometimes cases we can show that I guess, so general transformation f of x minus f of y smaller than L of x minus y. When L equals to 1, this is called non-expansion. When L is strictly smaller than 1, this is called contraction. So if this f is update rule of your parameter, and y you keep setting this y to be the optimal parameter, then this is saying that if you keep doing this, if this is a contraction, then you end up getting the linear convergence. So the operator theoretical form is a very nice way for you to work out the convergence of the strongly convex case of the variance of these proximal gradient methods that leads to the linear convergence. And the contraction factor, and this contraction factor L parameter naturally would correspond to something that looks like 1 minus 1 over the condition number kappa, or if accelerated, 1 minus square root of 1 over the condition number kappa. Okay, that's I guess that's the end of today's lecture. So it's a lot of materials, and you don't have to know everything. And it's you've seen that this is a very interesting branch of mathematics, that everything seems to be related to everything else. And the more interesting part for the interest of this lecture and for our class in terms of computation is how we can make use of this beautiful mathematics to construct algorithms and analyze this algorithm so that we can show interesting properties about things that are not known before, like in your, for instance, in your research. And even to simply applying some of these smoothing techniques to your problem can lead to orders of magnitude of improvement in how quickly you can design algorithms to solve your problem. So I'll leave it here and then use the next 10 minutes to address any questions that you guys may have.